Classical mechanics is beautiful in its simplicity. If you know where something is and how fast it's moving, you can predict exactly what it will do next. Newton gave us the equations, and for centuries they worked perfectly. A ball thrown into the air, a planet orbiting a star, a pendulum swinging back and forth. Give me the initial conditions, and I'll tell you the future with absolute certainty. Then, quantum mechanics came along and shattered everything. But here's the twist that nobody tells you. Quantum mechanics is actually just as deterministic as classical mechanics, just as beautiful, just as elegant. If you know the quantum state of a particle, its wave function, you can use the Schrödinger equation to calculate exactly what that particle will do in the future. Watch this. This is a real solution to the Schrödinger equation, computed frame by frame. The wave function spreads out smoothly, continuously, predictably. No randomness, no dice-throwing gods. Pure mathematical. Evolution. So why does everyone think quantum mechanics is random? Why do physicists talk about probability and uncertainty as if they're fundamental features of reality? Because of what happens when we look. When we measure a quantum particle, we don't see this beautiful spreading wave. We see a dot, a single point. The particle is here, not there. One location, one outcome. And here's where things get strange. That spreading wave we just watched, the one evolving so smoothly under the Schrödinger equation, somehow suddenly collapses into a single point the moment we observe it. Poof, gone. All that mathematical elegance, all that smooth evolution, replaced by an abrupt, discontinuous jump to a single location. This is the measurement problem, and it's been haunting physics for nearly a century. Think about how bizarre this is. We have one set of rules for when we're not looking. The wave function evolves according to the Schrödinger equation, spreading out, interfering with itself, doing all sorts of wave-like things. Beautiful, predictable, deterministic. Then we have a completely different set of rules for when we are looking. The wave function collapses. Randomly, instantly, irreversibly. The probability of finding the particle at any particular location is given by the amplitude of the wave function at that point, squared. This is the Born rule, named after physicist Max Born, who proposed it in 1926. And here's a fun fact. The Born rule, this foundational principle that introduces probability into the very fabric of reality, first appeared as a footnote. A footnote. Born had written a paper about quantum collisions, and almost as an afterthought, he added a note at the bottom of the page suggesting that if you square the amplitude of the wave function, you get the probability of finding the particle there. That footnote changed everything. It made quantum mechanics fundamentally probabilistic. No longer could we predict with certainty what would happen. The best we could do was calculate the odds. Einstein hated this. Actually, hated it. He famously wrote to Born saying he was convinced God does not play dice. And you know what? Einstein had a point. It does seem weird that the universe would have two completely different sets of rules. Smooth evolution when nobody's watching. Sudden collapse when somebody is. Who decides what counts as watching? What makes a measurement special? Is it consciousness? Is it the size of the measuring device? Is it some magic threshold where quantum effects suddenly stop applying? Nobody could give a satisfying answer. But the Born rule worked. It worked spectacularly. Every prediction it made matched experimental results perfectly. So physicists did what physicists do when something works but doesn't make sense. They shut up and calculated. They stopped asking why and focused on how. This approach, often called the Copenhagen interpretation after the city where Niels Bohr worked, became the standard way of teaching quantum mechanics. It's probably how you learned it, if you learned it at all. the wave function evolves according to the Schrödinger equation until you measure it, then it collapses according to the Born rule. Don't ask what the wave function really is. Don't ask why measurement is special. Don't ask when exactly the collapse happens. Just calculate probabilities and compare them to experiments. And for most practical purposes, this works fine. If you're an engineer building quantum computers or a chemist studying molecular bonds, you don't need to worry about the philosophical implications of wave function collapse. You just need to calculate the right answers, and Copenhagen gives you those answers. But some physicists couldn't let it go. Couldn't accept that reality might be fundamentally random, or that measuring something should be treated differently from any other physical process. One of those physicists was Erwin Schrödinger himself, the man who wrote the equation that bears his name. In 1935, Schrödinger published a paper with a thought experiment that would become one of the most famous ideas in all of physics. Everyone's heard of Schrödinger's cat. Most people think it's meant to show how weird quantum mechanics is, how strange and counterintuitive the quantum world can be. A cat that's simultaneously alive and dead. Quantum superposition at the scale of everyday objects, mind-bending stuff. But that wasn't Schrödinger's point at all. He wasn't trying to celebrate the weirdness of quantum mechanics. He was trying to show that quantum mechanics, as formulated by the Copenhagen interpretation, was wrong. Let me walk you through his argument. Start with a cat in a box. Also in the box is a tiny amount of radioactive material, maybe a single atom, connected to a radiation detector. The detector is hooked up to a mechanism that will smash a flask of poisonous cyanide gas if radiation is detected. Schrödinger notes, somewhat darkly, that this device must be secured against direct interference by the cat. Now, according to quantum mechanics, that radioactive atom doesn't have to be either decayed or not decayed. Generally, it exists in a superposition of both states at once, both decayed and not decayed, simultaneously. This might sound like nonsense, but it's a direct consequence of the Schrödinger equation. The wave function of the atom spreads out over time to encompass both possibilities. Now, here's where things get interesting. The state of the detector is directly tied to the state of the atom. If the atom has decayed, the detector clicks and releases the poison. If the atom hasn't decayed, the detector stays silent and the poison stays contained. The detector and the atom are entangled. We'll talk more about entanglement later, but for now, just understand that they're connected. Their fates are linked. But the detector is also entangled with the cat. If the detector clicks, the cat dies. If the detector doesn't click, the cat lives. So the state of the cat is directly tied to the state of the detector, which is directly tied to the state of the atom. And since the atom is in a superposition of decayed and not decayed, the detector must be in a superposition of clicked and not clicked, which means the cat must be in a superposition of dead and alive. Not dead or alive. Dead and alive. Both. Simultaneously. According to the mathematics of quantum mechanics, before we open the box and look inside, the cat genuinely is in a superposition of alive and dead. Only when we make a measurement, when we open the box and observe the cat, does the wave function collapse and the cat become definitely one or the other. Now, most people hear this and think, okay, quantum mechanics is weird. Cats can be alive and dead at the same time. That's just how it is at the quantum scale. But Schrödinger wasn't saying this to show how cool and strange quantum mechanics is. He was saying this to show how absurd the Copenhagen interpretation is. He's basically arguing, look, you're telling me that this cat really is both alive and dead until someone looks? That's ridiculous. Cats are not both alive and dead. That's not how reality works. If your theory predicts that cats exist in superpositions of life and death, then your theory is wrong. There must be something incorrect about the way we're thinking about quantum mechanics. The problem is, which part is wrong? Schrödinger's cat experiment involves three key quantum concepts: superposition, the idea that quantum systems can be in multiple states at once; entanglement, the idea that quantum systems can be linked such that the state of one depends on the state of another; and measurement, the idea that observing a quantum system causes its wave function to collapse from a superposition into a definite state. One of these three concepts must be flawed, or at least misunderstood, for the cat to make sense. So let's examine each one carefully, starting with superposition. Is it really true that quantum objects can be in two different states at the same time? This seems like the most obviously crazy part of quantum mechanics. Nothing in our everyday experience behaves this way. A coin is either heads or tails. A light switch is either on or off. You're either in your kitchen or your bedroom, not both simultaneously. How can a particle be in two places at once? How can an atom be both decayed and not decayed? It sounds like word salad. But here's the thing. We have direct experimental evidence that superposition is real. The double-slit experiment proves it beyond any doubt. Here's how it works. Take a source that fires individual electrons, one at a time, toward a barrier with two narrow slits cut into it. Behind the barrier is a screen that lights up wherever an electron hits it. Fire one electron. It goes through the slits and hits the screen at some point. Fire another electron. It hits a different point. Fire thousands of electrons, one by one, and gradually a pattern builds up on the screen. Now, if electrons were simply particles, little balls following definite paths, you'd expect a simple pattern. Some electrons would go through the left slit and pile up in one spot. Other electrons would go through the right slit and pile up in another spot. You'd see two bright bands on the screen, one behind each slit. But that's not what happens. Instead, you see an interference pattern. Multiple bright and dark bands across the screen. Bright where lots of electrons hit. Dark where almost no electrons hit. This is the pattern you get from waves, not particles. When a wave passes through two slits, it diffracts, spreading out beyond each slit. The wave from the left slit and the wave from the right slit overlap and interfere with each other. Where two peaks meet, you get constructive interference and a bright band. Where a peak meets a trough, you get destructive interference and a dark band. But here's what makes this truly mind-bending. We're firing individual electrons, one electron at a time. There's never more than one electron traveling through the apparatus at once. Yet we still get the interference pattern. Each individual electron somehow goes through both slits simultaneously. It has to. That's the only way to explain the interference pattern. The electron isn't taking a definite path through one slit or the other. It's in a superposition of both paths. Its wave function spreads out and passes through both slits at once, then interferes with itself before hitting the screen. And just to make this even more bizarre, if you try to measure which slit the electron goes through, if you put detectors at the slits to see which one the electron passes through, the interference pattern disappears. The moment you measure which path the electron takes, it stops acting like a wave in superposition and starts acting like a particle with a definite location. The act of measurement changes the outcome. This isn't a thought experiment. This is real. This has been done thousands of times with electrons, photons, atoms, even large molecules. The results are always the same. Quantum objects in superposition create interference patterns. The double-slit experiment is concrete, undeniable proof that superposition is real. And it makes sense when you think about it in terms of waves. Waves are naturally spread out in space. A water wave doesn't exist at just one point. It exists across a region. It can easily pass through two slits simultaneously because it's not localized to begin with. And we know that when we're not looking at them, when we're not measuring them, quantum particles are represented by waves, the wave function. that spreading, evolving mathematical object we saw at the beginning. The double-slit experiment shows that this wave isn't just a mathematical trick. It represents something real and physical, something that enables individual electrons to pass through both slits at the same time. So, superposition is on solid ground. It's been verified experimentally countless times. It's not the weak link in Schrödinger's cat. Which brings us to the second concept, entanglement. Entanglement might be the most counterintuitive concept in all of quantum mechanics, and that's really saying something. Einstein called it spooky action at a distance, and he meant it as a criticism. He thought entanglement was so bizarre, so incompatible with how reality should work, that it proved quantum mechanics must be incomplete. Turns out Einstein was wrong about this one, but his instinct about how strange entanglement is was absolutely correct. Let me show you what entanglement really means. Imagine two electrons fired toward each other with equal and opposite velocities. They're going to collide. When they do, they'll scatter off each other and fly away in new directions. Now, if these were classical particles like billiard balls, we could measure their positions and velocities before the collision, plug those numbers into Newton's equations, and calculate exactly what happens. Where each electron goes, how fast it's moving, everything. Perfect prediction. But these are quantum particles, which means before we measure them, their positions and velocities aren't definite. Each electron is represented by a wave function, a spread-out probability distribution. We can't say exactly where each electron is or how fast it's moving. We can only give probabilities, so when these two electrons collide, we don't know exactly what will happen. Their trajectories after the collision are given by spread-out wave functions. Lots of possible outcomes, each with some probability. But here's the crucial part. Even though we don't know the exact outcome, we do know that momentum must be conserved. This isn't some quantum weirdness. This is a fundamental law of physics that applies to everything, classical or quantum. Whatever momentum one electron gains, the other must lose. If one electron scatters to the left with some momentum, the other must scatter to the right with equal and opposite momentum. The total momentum before the collision must equal the total momentum after. So imagine we let these two electrons scatter and fly far apart. Light years apart, if you want. We don't measure them. We just let them travel through space, each one's wave function spreading out, encompassing more and more possible positions and momenta. Now we measure one of the electrons. We find it at some position, moving with some velocity. The wave function of that electron collapses from a spread-out probability wave to a definite state. But here's the weird part. The moment we measure the momentum of that one electron, we instantly know the momentum of the other one. It has to be equal and opposite. Otherwise, momentum conservation would be violated. So, by measuring one electron, we've instantly determined the state of the other electron, even though it might be light years away, even though we never touched it, even though no signal could possibly have traveled between them in the time it took us to make the measurement. This is what Einstein found so troubling. It seems like information is being transmitted faster than light. Measure one electron here, and instantly, immediately, without any time delay whatsoever, the state of the other electron changes over there. How is that possible? How can measuring one particle affect another particle instantaneously across vast distances? It seems to violate everything we know about causality and the speed of light. But here's the thing. Before we measured the first electron, we said that each electron's momentum was uncertain, given by a spread-out wave function of probabilities. But that's not quite right. It's more accurate to say that after the collision, the two electrons don't have separate wave functions at all. They share a single wave function, one mathematical object that describes both electrons together. This is what it means to be entangled. After two quantum systems interact, they're no longer independent. You can't describe one without describing the other. They're connected, linked, bound together by a single wave function. And this explains why measuring one electron instantly affects the other. It's not that some signal is traveling between them, it's that they're described by a single wave function, and when that wave function collapses, it collapses everywhere at once. Think of it like this. Imagine a long rope stretched between two people. If one person shakes their end of the rope, creating a wave, that wave travels down the rope to the other person. Information is transmitted at some finite speed, the speed of the wave along the rope. But now imagine instead that the rope is the wave function itself, and both electrons are just different parts of that same wave. When you collapse the wave function by measuring one electron, you're not sending a signal from one electron to the other. You're collapsing the entire wave, everywhere, all at once. Both electrons are part of the same quantum state, so measuring one necessarily affects both. This is entanglement. And once you understand this, you realize that entanglement should be everywhere. Anytime two quantum systems interact, they become entangled. The atoms in your body are constantly colliding with each other, with photons, with air molecules. Every collision creates entanglement. Every interaction links quantum systems together into larger and larger entangled states. In fact, if we're being really rigorous about this, we should say that there's only one wave function, the wave function of the entire universe. Every particle that's ever interacted with any other particle is entangled with it, and those particles are entangled with others and so on, creating this vast web of quantum correlations that connects everything in the universe into a single, unified quantum state. Now, in practice, we don't have to worry about this most of the time. If two particles are sufficiently isolated, if they haven't interacted with each other or with any of the same particles, we can reasonably talk about their separate wave functions. It's a good approximation. But strictly speaking, it's not correct. Strictly speaking, everything is entangled with everything else. The universe is one big quantum system described by one enormous wave function. But here's the key insight. This doesn't make entanglement mysterious or problematic. It makes it natural, inevitable. Of course, particles that interact become entangled. Of course, they end up sharing a single wave function. That's just what happens when quantum systems collide. The Schrödinger equation tells us exactly how wave functions evolve when particles interact, and entanglement is the automatic result. So, entanglement, weird as it seems, is actually perfectly well understood. It's a fundamental part of quantum mechanics, describing how systems evolve according to the Schrödinger equation. And, like superposition, entanglement has been verified experimentally thousands of times. We can create entangled particles in the lab and confirm that measuring one instantly determines the state of the other, even when they're separated by large distances. In fact, this property of entanglement is now being used to build quantum computers and quantum communication systems. Entanglement isn't just theoretically interesting, it's technologically useful. So we've examined two of the three key concepts in Schrödinger's cat. Superposition is real. Entanglement is real. Both are fundamental features of quantum mechanics that have been experimentally verified beyond any doubt. Which leaves only one suspect: measurement. This is where things get interesting. Because unlike superposition and entanglement, which are natural consequences of the Schrödinger equation, measurement is something we had to add to quantum mechanics by hand. Remember those two sets of rules I mentioned at the beginning? When you're not looking, the wave function evolves smoothly according to the Schrödinger equation. When you are looking, when you make a measurement, the wave function collapses according to the Born rule. These are completely different processes. The Schrödinger equation is deterministic, continuous, reversible. You can run it forward in time or backward in time and get consistent results. Wave function collapse is random, discontinuous, irreversible. The wave function suddenly jumps from a superposition to a definite state, and you can never go back. So quantum mechanics has this weird split personality. Two entirely different mechanisms for how quantum systems evolve, and the boundary between them is vague and poorly defined. What counts as a measurement? Does it require a conscious observer? Does it require a classical measuring device? How big does the measuring device have to be? When exactly does the wave function collapse? These questions don't have clear answers in the Copenhagen interpretation, and that should bother us. It bothered Einstein. It bothered Schrödinger. And it should bother you. Because when you really think about it, measurement is just an interaction between two quantum systems. One system is the thing being measured, like an electron. The other system is the measuring device, like a detector. And detectors are made of atoms. Atoms are quantum mechanical. They have wave functions. They obey the Schrödinger equation. So when an electron hits a detector, that's just two quantum systems interacting. We know exactly how to describe interactions between quantum systems. Their wave functions become entangled. The Schrödinger equation tells us precisely how. There's no collapse. There's no randomness. There's just smooth, continuous evolution of the combined wave function. So why do we treat measurement as something special? Why do we say that when an electron interacts with a detector, something different happens compared to when an electron interacts with another electron? Why the double standard? Now, you might argue that detectors are macroscopic objects, not individual particles, and maybe that makes a difference. Maybe when you have trillions and trillions of atoms all acting together, quantum effects average out, and you get classical behavior. And there's some truth to this. Large objects do tend to behave classically. But classically doesn't mean the Schrödinger equation stops applying. It means that quantum effects become very hard to observe. The wave function is still there. It's still evolving according to the Schrödinger equation. It's just that the superpositions involved are so complex and so spread out that they look classical to us. So the question remains. If detectors are made of atoms, and atoms obey the Schrödinger equation, why should we treat the detector interacting with an electron any differently from any other quantum interaction? And here's an even more troubling question. What about us? We're made of atoms too. Our brains, our eyes, our entire bodies are collections of electrons and protons and neutrons, all obeying the laws of quantum mechanics. When we observe a quantum system, we're not doing something magical or special. We're just another quantum system interacting with it. Our atoms are getting entangled with its atoms. So if we're quantum mechanical, and the measuring device is quantum mechanical, and the particle being measured is quantum mechanical, why should observation cause a wave function collapse? Who or what is doing the collapsing? This is the measurement problem, and it's been plaguing quantum mechanics since the beginning. The Copenhagen interpretation just sweeps it under the rug by declaring that measurement is special without explaining why or how. But what if we took a more radical approach? What if we said that measurement isn't special at all? What if we threw out the entire concept of wave function collapse and said that wave functions always, without exception, evolve according to the Schrödinger equation? No collapse, no Born rule. Just the Schrödinger equation all the time, for everything. This might seem like a crazy idea. After all, we see wave functions collapse. When we measure an electron, we find it at a definite position, not spread out as a wave. That looks like collapse. But remember, we're quantum mechanical too. So, when we interact with an electron, we don't stand outside the system observing it. We become entangled with it. Our wave function and the electron's wave function merge into a single, larger wave function. And here's where things get really interesting. let's go back to Schrödinger's cat and walk through what happens if we take this approach seriously. Start with the radioactive atom in the box. It's in a superposition of decayed and not decayed. This is fine. Superposition is real. The atom's wave function evolves according to the Schrödinger equation, spreading out over time to encompass both possibilities. The detector is connected to the atom. When the atom decays, it emits a particle that hits the detector, causing it to click. When the atom doesn't decay, no particle is emitted and the detector stays silent. So the detector becomes entangled with the atom. Its state depends on the atom's state. The detector's wave function and the atom's wave function merge into a single combined wave function describing both. And this combined wave function is in a superposition. Part of it describes the atom has not decayed, and the detector has not clicked. Another part describes the atom has decayed, and the detector has clicked. Both states exist simultaneously in the wave function. The detector is in a superposition of having clicked and not clicked, just like the atom is in a superposition of having decayed and not decayed. Now, the detector is connected to the flask of poison. If the detector clicks, the flask smashes and releases cyanide. If the detector doesn't click, the flask stays intact. So, the flask becomes entangled with the detector. Its state depends on the detector's state. The wave function describing the atom, detector, and flask is now in a superposition of atom not decayed, detector not clicked, flask intact and atom decayed, detector clicked, flask smashed. The cyanide, if released, spreads through the box and is inhaled by the cat. If the flask is intact, the cat breathes normally. So the cat becomes entangled with the flask, which is entangled with the detector, which is entangled with the atom. The wave function now describes the entire system: atom, detector, flask, cat. And this wave function is in a superposition. Part of it describes atom not decayed, detector not clicked, flask intact, cat alive. Another part describes atom decayed, detector clicked, flask smashed, cat dead. The cat is in a superposition of alive and dead. This is what the mathematics tells us. But here's the crucial point. We haven't invoked wave function collapse yet. We've just been applying the Schrödinger equation, letting everything evolve smoothly and continuously. The superposition isn't a problem. It's just what happens when quantum systems interact and become entangled. Now you walk up to the box and open it. You're about to observe the cat. In the Copenhagen interpretation, this is when the wave function collapses. The cat suddenly becomes either definitely alive or definitely dead, with probabilities given by the Born rule. But we're not using the Copenhagen interpretation anymore. We're only using the Schrödinger equation. So what happens when you open the box? You become entangled with the system. Your atoms interact with the photons bouncing off the cat, which carry information about whether the cat is alive or dead. Those photons hit your retinas, triggering chemical reactions in your neurons, which propagate signals through your brain. Every step of this process is just quantum systems interacting, particles colliding, wave functions merging, entanglement spreading. And now the wave function describes you too. It's in a superposition. Part of it describes atom not decayed, detector not clicked, flask intact, cat alive, you see a living cat. Another part describes atom decayed, detector clicked, flask smashed, cat dead, you see a dead cat. You are in a superposition of seeing a living cat and seeing a dead cat. Both states exist simultaneously in the wave function. Now, at this point, you're probably objecting. Wait a minute, you're saying. I've never seen a superposition. I've never observed a cat that was both alive and dead. When I look at something, I see one outcome, not multiple outcomes simultaneously. How can you claim I'm in a superposition when my experience is definitely one thing or the other? And this is the key insight. The insight that explains everything. You are in a superposition. But the version of you that saw the cat alive and the version of you that saw the cat dead are no longer the same person. They've diverged. They inhabit separate realities, separate worlds. Think about it this way. Before you opened the box, there was one you, one unified wave function describing your quantum state. But when you became entangled with the superposition inside the box, your wave function split. It branched into two separate parts, two separate versions of you. One version saw the cat alive. That version's brain state, memories, and experiences all reflect having observed a living cat. The other version saw the cat dead. That version's brain state, memories, and experiences all reflect having observed a dead cat. Both versions exist. Both are equally real. Both emerged from the same original you. But they're not you anymore. They're two different people now, with slightly different memories and experiences. And here's the really wild part. They can never communicate with each other. They inhabit separate branches of the wave function, separate worlds. The branch where the cat is alive and the branch where the cat is dead have no way to interact. They've separated, split off, become independent. So from your perspective, from the inside, it looks like only one outcome happened. You saw either a living cat or a dead cat, not both. But that's because you only experience one branch of the wave function. The you that saw the living cat has no access to the branch where the cat died. The you that saw the dead cat has no access to the branch where the cat lived. Each version of you thinks they're the only one. But both versions exist. So the cat isn't alive and dead simultaneously from any observer's perspective. The cat is alive in one world and dead in another world. Both worlds are real. Both exist as parts of the universal wave function. We just don't experience both because we're stuck in one branch. This is the many worlds interpretation of quantum mechanics. The many worlds interpretation was formulated by a physicist named Hugh Everett in 1957. He was a graduate student at Princeton at the time, working under the supervision of John Wheeler, one of the giants of 20th century physics. Everett was troubled by the measurement problem, by this arbitrary division between when the Schrödinger equation applies and when wave function collapse applies. He thought there had to be a better way. So he proposed something radical. What if the wave function never collapses? What if the Schrödinger equation is all there is? No additional rules. No special treatment for measurement. Just wave functions evolving smoothly and continuously according to the same equation, always, everywhere, without exception. At first, this seems impossible. We see collapses. We see definite outcomes. But Everett realized that if you take the Schrödinger equation seriously and apply it to everything, including observers, you naturally get branching. You get multiple worlds. Not because you're adding something to quantum mechanics, but because you're taking away the artificial collapse postulate. The worlds are already there in the mathematics. They've always been there. The founders of quantum mechanics just refused to take them seriously. Everett called his idea the relative state formulation, because the state of any system is only defined relative to the state of the observer. There's no absolute collapse, no single outcome that everyone agrees on. Different observers can have different relative states, corresponding to different branches of the wave function. Later, physicist Bryce DeWitt popularized Everett's work and coined the term many worlds interpretation, which is the name that stuck. But calling it many worlds makes it sound like you're adding something extravagant to quantum mechanics. Multiple universes spawning out of nowhere. Infinite copies of reality. It sounds like science fiction. But that's backwards. Many worlds isn't adding anything. It's removing something. It's getting rid of wave function collapse, this extra mechanism that was bolted onto quantum mechanics to make it match our everyday experience. When you remove collapse, when you just use the Schrödinger equation, the multiple worlds fall out naturally. They're not an assumption, they're a consequence. Think of it this way. In the Copenhagen interpretation, you have wave functions evolving according to the Schrödinger equation, plus you have wave function collapse happening during measurements. Two mechanisms, two sets of rules. In many worlds, you have wave functions evolving according to the Schrödinger equation. One mechanism, one set of rules. Which is simpler? Which is more elegant? Which requires fewer assumptions? Many worlds is actually the more conservative interpretation. It takes quantum mechanics as it is, with just the Schrödinger equation, and asks what that implies. The answer is branching, multiple worlds. And our inability to see those other worlds isn't because they don't exist. It's because we're entangled with one particular branch and can't access the others. Now, I know what you're thinking. This sounds absurd. Utterly, completely absurd. Every time a quantum measurement happens, the universe splits into multiple copies? There are countless versions of me out there, living slightly different lives? That's impossible. That's insane. But here's the thing. Your experience would be exactly the same whether many worlds is true or whether wave functions actually collapse. Think about it. In Copenhagen, you measure an electron, and its wave function collapses. You see one outcome. In many worlds, you measure an electron, and your wave function branches. One version of you sees one outcome, another version sees a different outcome. But each version thinks they saw the only outcome. From the inside, from the perspective of any individual observer, these two interpretations are indistinguishable. You can't tell which one is true based on what you experience. The difference is philosophical, not experimental. So, if both interpretations give the same predictions, why should we prefer one over the other? Because many worlds is mathematically simpler. It doesn't require adding wave function collapse to the theory. It just uses the Schrödinger equation that was already there. And in physics, we have a principle called Occam's razor. When two theories make the same predictions, prefer the simpler one, the one that requires fewer assumptions. By that standard, many worlds wins. But there's another reason to take many worlds seriously. It restores determinism to physics. Remember how I said at the beginning that quantum mechanics is deterministic? If you know the wave function, you can use the Schrödinger equation to calculate exactly what it will do in the future. No randomness, no probability. The wave function evolves in a completely predictable way, but Copenhagen adds randomness through the collapse postulate. When you measure a particle, you get a random outcome with probabilities given by the Born rule. The universe is fundamentally probabilistic. Many worlds says no, the universe is still deterministic. The wave function evolves according to the Schrödinger equation, always. Every possible outcome of a measurement actually happens. It just happens in different branches, so there's no randomness at the level of the universal wave function. The randomness we perceive is just because we only see one branch. We don't know which branch we'll end up in, so from our perspective, it looks random. But from the perspective of the universe as a whole, everything that can happen does happen. 100% of the time, with absolute certainty. Some physicists find this deeply satisfying. The universe operates according to a single, elegant equation. No exceptions, no collapse, no randomness. Just the Schrödinger equation, playing out its consequences. Other physicists find it deeply disturbing. The price of determinism is accepting that countless other versions of you exist, making different choices, experiencing different outcomes, and you'll never know anything about them. But whether we find it satisfying or disturbing doesn't change whether it's true. Reality doesn't care about our aesthetic preferences. So let's dig deeper into how this branching actually works, because there's a subtlety here that's easy to miss. When does branching happen? What causes it? In the cat experiment, I described branching as happening when you open the box and observe the cat. But that's not quite right. The branching actually happened much earlier. It happened the moment the detector became entangled with the atom. Let me explain. The detector isn't just the device connected to the atom. The detector is made of atoms, and those atoms are constantly colliding with air, molecules in the box. Photons are bouncing off the detector's surface. The atoms in the detector are vibrating, bumping into each other. Every one of these interactions creates entanglement. The detector's state becomes entangled with the state of the air molecules, with the state of the photons, with the state of everything it touches. This is called environmental decoherence. The quantum system, the detector, interacts with its environment, all the particles around it that we're not keeping track of. And when a quantum system in a superposition becomes entangled with its environment, something interesting happens. The different parts of the superposition separate. They stop interfering with each other. They become effectively different worlds. Here's a more realistic picture of the cat experiment. The atom starts in a superposition of decayed and not decayed. So far, so good. The detector becomes entangled with the atom. Now the detector is in a superposition of clicked and not clicked. Still good. But immediately, within an incredibly short time, the detector starts interacting with the environment. Air molecules bounce off it. Photons hit it. The vibrations in its atoms spread to nearby atoms. And because the detector is in a superposition, these environmental particles become entangled with that superposition. An air molecule that bounces off the detector will scatter differently depending on whether the detector clicked or not. Its trajectory depends on the detector's state. So the air molecule becomes entangled with the detector. Its wave function branches. One part describes the molecule scattering one way, corresponding to the detector having clicked. Another part describes the molecule scattering another way, corresponding to the detector not having clicked. But that air molecule collides with other air molecules, and those molecules collide with others. And within an absolutely tiny fraction of a second, trillions upon trillions of particles have become entangled with the detector's state. The superposition has spread throughout the environment. And once that happens, once the environment is entangled, the two parts of the superposition, detector clicked and detector not clicked, stop interfering with each other. They've effectively split into separate worlds. The branching has happened. And this all occurs essentially instantaneously, long before you open the box. By the time you walk up and look inside, the universe has already branched into one world where the cat is alive and one world where the cat is dead. Opening the box doesn't cause the branching. It just tells you which branch you're in. You were split into two versions long before you opened the box. The version of you that's about to see a living cat and the version that's about to see a dead cat. Both exist. Both are walking toward the box. Both are about to look inside. They just don't know they're separate yet because they haven't interacted with the system inside the box. But they will. And when they do, their memories will diverge. Their experiences will differ. They'll become genuinely different people. This is environmental decoherence, and it's absolutely crucial to understanding many worlds. Branching doesn't happen because of conscious observation. It happens because of interaction with the environment. Any quantum system in a superposition will undergo decoherence as soon as it starts interacting with lots of uncontrolled particles. And in our world, everywhere except in extremely carefully controlled lab conditions, quantum systems are constantly interacting with their environment, which means decoherence is happening all the time, constantly, at an absolutely staggering rate. Every radioactive decay, every particle collision, every absorption of a photon, all of these create superpositions that immediately decohere and branch. The universe is splitting, constantly, into an enormous number of branches. Now, how enormous? How many worlds are there? How often does branching happen? Honestly, we don't know. We don't even know if the number is finite or infinite. Let me give you some numbers to illustrate the scale. Your body contains radioactive isotopes, mostly carbon-14 and potassium-40. These isotopes decay at a steady rate. In your body, radioactive nuclei are decaying about 5,000 times per second. Each of those decays is a quantum event. The nucleus is in a superposition of decayed and not decayed. When it interacts with its environment, that superposition decoheres. The universe branches. One branch where the nucleus decayed, one branch where it didn't. So, just from radioactive decay in your body alone, the universe is branching thousands of times every second. And that's just you. Every person on Earth has radioactive atoms decaying. Every animal, every plant, the ground beneath your feet is slightly radioactive. The air you breathe contains radioactive isotopes. The cosmic rays streaming down from space are triggering nuclear reactions in the atmosphere constantly. Add it all up, and the number of branching events happening on Earth every second is truly astronomical. And Earth is just one tiny speck in a vast universe. So the total branching rate across the entire observable universe is almost unimaginably large. But here's the thing. We don't actually know how many branches there are because we don't know whether the underlying structure of reality is discrete or continuous. If space and time are fundamentally discrete, made of tiny indivisible chunks, then the number of possible quantum states is huge, but finite. That would mean the number of branches is enormous but finite. On the other hand, if space and time are truly continuous, infinitely divisible, then the number of possible quantum states is literally infinite. And that would mean the number of branches is also infinite. Infinite copies of you, making every possible decision, experiencing every possible outcome. We don't know which picture is correct because we don't have a complete theory of quantum gravity. We don't understand the ultimate structure of space and time at the smallest scales. So, the number of worlds in many worlds is somewhere between absolutely enormous and literally infinite. That's the best answer we can give right now. But does it matter? Whether there are 10 to the power of a billion branches or infinitely many, the basic picture is the same. The wave function of the universe is constantly branching into separate, non-interacting parts. Each branch contains observers who think they're experiencing the only reality. But they're not. They're just experiencing one branch among countless others. Now, let's address another common misconception about many worlds. People often say that in many worlds, everything that could possibly happen does happen. Every conceivable outcome, no matter how unlikely, occurs in some branch. You win the lottery in one world. You become president in another. You get struck by lightning while simultaneously being attacked by a shark in yet another. But this isn't quite right. Many worlds doesn't mean everything possible happens. It means everything that the Schrödinger equation predicts can happen does happen. And the Schrödinger equation has rules. It doesn't allow just any old thing. For example, an electron will never spontaneously turn into a proton. That would violate conservation of electric charge. The Schrödinger equation gives that event a probability of exactly 0. So there's no branch where it happens. Similarly, you'll never see a ball roll uphill and gain energy for no reason. That would violate conservation of energy. The Schrödinger equation forbids it. no branch where that happens. The laws of physics still apply in many worlds. In fact, they apply even more strictly because there's no wave function collapse to introduce randomness. Everything evolves according to the deterministic Schrödinger equation, which respects all the conservation laws. So yes, there are branches where unlikely things happen. Branches where you win the lottery. Branches where you become president. These are low probability events, but they have non-zero probability according to quantum mechanics, so they happen in some branches. But there are no branches where impossible things happen, where electrons turn into protons or energy appears from nowhere. The structure of the wave function, the rules encoded in the Schrödinger equation, prevent those outcomes. So many worlds is constrained by the same physical laws as any other interpretation of quantum mechanics. It just says that all the outcomes allowed by those laws actually occur in different branches. Another question people often ask is about personal identity. If the universe is constantly branching and creating copies of me, which one is the real me? Are all the copies me, or are they different people? This is a deep philosophical question, and I'm not sure there's a definitive answer. But here's how I think about it. Right now, at this moment, there's one you, one unified consciousness, one set of memories and experiences. But quantum mechanics, if many worlds is correct, tells us that your wave function is about to branch. Maybe in the next microsecond. Maybe it already has, countless times while you've been reading this. When your wave function branches, two slightly different versions of you emerge. At the moment of branching, they're nearly identical. Same memories, same thoughts, same personality. But as time goes on, they'll have different experiences. They'll observe different outcomes of quantum measurements. Their memories will diverge. Their thoughts will diverge. Eventually, they might make different decisions, take different paths in life. At what point do they stop being you and become different people? I don't think there's a sharp boundary. It's like asking at what point a child stops being a child and becomes an adult. It's gradual, fuzzy, a matter of degree rather than a clear dividing line. What's clear is that both versions emerged from you. Both have an equal claim to being the continuation of your consciousness. Neither is more real or more legitimate than the other, and from the inside, from the subjective experience of each version, they each feel like the one true continuation of you. They remember being you. They think of themselves as you. So, in some sense, they both are you. It's just that you've split into multiple people who each think they're the only one. This might sound disturbing. The idea that you're constantly splitting into countless copies, most of whom you'll never know about, living lives you'll never experience. But remember, if many worlds is true, this has been happening your entire life. It's been happening since the moment you were born. Since before you were born. Your parents split into multiple versions, and you exist in multiple branches. You've always been branching. You just didn't know it. And knowing it doesn't change anything about your subjective experience. You still experience one continuous timeline, one sequence of events. The branching is invisible to you. So, in practice, you can just live your life as if there's only one world, your world. The other branches, the other versions of you, are real in some ultimate sense, but they're not part of your experience. They might as well not exist, as far as you're concerned. Though I suppose it's mildly comforting to know that in some branches, I made better decisions than I did in this one. Now let's talk about probability. This is where many worlds gets really interesting and, honestly, a bit tricky. In the Copenhagen interpretation, probability is fundamental. When you measure a quantum system, you get one outcome, chosen at random according to the Born rule. The probability of each outcome is given by the square of the wave function's amplitude. But in Heidan's many worlds, every outcome happens. You see all the outcomes, just in different branches. So where does probability come in? If every possibility is realized, what does it mean to say one outcome is more probable than another? This is called the probability problem in many worlds, and it's been debated for decades. Here's the issue. Suppose you have a quantum measurement with two possible outcomes. In Copenhagen, outcome A has a 70% probability, and outcome B has a 30% probability. You do the measurement, and you get either A or B with those probabilities. In many worlds, you do the measurement, and both outcomes happen. One version of you sees A, another version sees B. Both versions exist. Both are equally real. So, in what sense is A more probable than B? Both happened. How can one be more likely than the other? The answer has to do with the amplitude of the wave function in each branch. Remember, probability is the square of the amplitude. If outcome A has a 70% probability, that means the amplitude of the part of the wave function corresponding to A is the square root of 0.7. If outcome B has a 30% probability, its amplitude is the square root of 0.3. Now, in many worlds, both branches exist, but they don't have equal weight. The branch where you see outcome A has a larger amplitude than the branch where you see outcome B. And amplitude, in many worlds, can be thought of as a measure of how much that branch contributes to the total wave function. It's like asking what fraction of reality that branch represents. The branch with 70% probability contains more of you, in some sense, than the branch with 30% probability. Now, this is getting a bit abstract and philosophical, so let me try to make it more concrete. Imagine you're going to do a quantum measurement with two outcomes, A and B. Outcome A has a 99% probability, outcome B has a 1% probability. In many worlds, both outcomes happen. But here's the key question. Before you do the measurement, before you know which branch you'll end up in, which outcome should you expect to see? Well, 99% of your future selves, weighted by amplitude, will see outcome A. Only 1% will see outcome B. So, if you're trying to predict your future experience, you should bet on seeing A, even though both outcomes will happen. This is how probability emerges in many worlds. It's not that only one outcome happens with some probability. It's that you don't know which branch you'll end up being in, and the amplitude of each branch tells you what fraction of your future selves will experience that outcome. High amplitude means most of your future selves see that outcome. Low amplitude means only a small fraction of your future selves see it. So, when we say an outcome has a high probability, we mean that most of your measure, most of your quantum amplitude, most of what makes you you ends up in branches where that outcome occurred. It's a statement about the distribution of your future selves across the branches, weighted by amplitude. This is a bit mind-bending, but it does recover the Born rule. It explains why we should expect to see outcomes with frequencies matching the squared amplitudes of the wave function. Even though all outcomes actually happen, the math works out. The predictions match experiment. So, many worlds is consistent with everything we observe. Despite its mathematical elegance and philosophical appeal, many worlds faces serious objections. Over the decades since Everett first proposed it, physicists have raised numerous concerns, and it's worth examining the most common ones carefully. The first and most visceral objection is simply this: where does all the energy come from? If the universe is constantly splitting into multiple copies, doesn't that require creating matter and energy out of nothing? Every time a branch occurs, we're duplicating the entire universe, right? All the galaxies, all the stars, all the particles. That's an incomprehensible amount of energy. Where does it come from? Doesn't this violate conservation of energy, one of the most fundamental laws of physics? This objection sounds devastating, but it's actually based on a misunderstanding of what branching means. The universe isn't duplicating itself. It's not creating new matter and energy. What's happening is more subtle. Think of it this way. Before a measurement, the wave function is in a superposition. It has some total energy. That energy is completely, absolutely, 100% conserved. The Schrödinger equation guarantees this. The energy of the total wave function never changes. But here's the key insight. After decoherence, after the branches separate, observers in each branch perceive only a fraction of that total energy. It's not that new energy was created, it's that the existing energy has been subdivided among the branches. Imagine you have a pizza. One whole pizza with 8 slices. Now, you cut the pizza in half and give one half to your friend. Have you created more pizza? No. You've taken the existing pizza and divided it into 2 pieces. Each piece is smaller than the original, but the total amount of pizza is conserved. Branching works the same way. You're not duplicating the wave function. You're subdividing it, taking one unified quantum state and splitting it into separate, non-interacting parts. Each part looks like a complete universe from the inside because it contains all the same types of particles and structures as before. But in terms of the universal wave function, each branch represents a smaller fraction of the total. The sum of all branches equals the original, unbranched wave function. Energy is perfectly conserved. Now, you might object that this doesn't match our experience. When I look around after a measurement, I see a complete universe with normal energy content. I don't feel like I'm in a depleted branch with less energy. But that's because energy is relative to the observer. From your perspective, within your branch, everything looks normal. You measure the mass of the sun, the energy of particles, the temperature of objects, and you get the expected values. But from the perspective of the universal wave function, your entire branch, everything you can ever observe or measure, contributes less to the total amplitude than it did before branching. The energy you perceive locally is conserved within your branch, and the energy of the universal wave function is conserved across all branches. There's no violation, no free energy appearing from nowhere. The mathematics is absolutely clear on this point. But the confusion is understandable because we're used to thinking of ourselves as outside observers looking at the whole system. In many worlds, we're inside the system. We're part of one branch, and we only see our branch's share of the total energy. The second major objection is about the sheer number of worlds. Even if energy is conserved, isn't it extravagant to propose countless, perhaps infinitely many, parallel universes? Isn't that violating Occam's razor in the most spectacular way possible? Shouldn't we prefer a theory that doesn't require an infinite multiverse? This objection also sounds compelling, but it misunderstands what Occam's razor actually says. Occam's razor tells us to prefer theories with fewer assumptions, not theories with fewer entities. It's about the simplicity of the theory's structure, not about how many things the theory says exist. Let me give you an example. In classical mechanics, we assume that space extends infinitely in all directions. That means there are infinitely many spatial points, an infinite number of locations where particles could be. Does this violate Occam's razor? Should we prefer a theory where space is finite? No, we prefer infinite space because it's simpler, mathematically. It doesn't have arbitrary boundaries. It doesn't require us to specify where space ends or what happens at the edge. The theory is simpler, even though it implies infinitely many spatial points. Many worlds is similar. Yes, it says there are many, perhaps infinitely many, branches of the wave function. But the theory itself is simpler than Copenhagen. Copenhagen requires the Schrödinger equation plus the collapse postulate plus the Born rule. 3 components. Many worlds requires only the Schrödinger equation. 1 component, fewer assumptions, simpler structure. The fact that this simpler structure implies many branches is not a problem. It's a consequence. And consequences don't count against a theory's simplicity. What counts is how many independent assumptions you need to make. By that standard, many worlds wins. It's the simpler theory. The fact that it predicts a multiverse is just what falls out of taking the Schrödinger equation seriously. Moreover, the branches in many worlds aren't really separate universes in the way science fiction depicts them. They're all part of one unified mathematical object, the universal wave function. It's like asking how many numbers exist. Well, there are infinitely many, but they're all part of one mathematical structure, the number line. Similarly, the branches are all part of one physical structure, the wave function. So talking about the number of worlds is somewhat misleading. There's one wave function that can be divided up into many branches for our convenience, but that division is somewhat arbitrary. Which brings me to the third objection. How many branches are there exactly? And how often does branching occur? We've talked about radioactive decays causing branching thousands of times per second, but is it really that discrete? Does the universe branch at specific moments, or is branching continuous? And if it's continuous, does that mean the branching rate is infinite? The honest answer is that we don't know. This is one of the open questions in many worlds. The mathematics of quantum mechanics tells us that decoherence occurs when a quantum system becomes sufficiently entangled with its environment. But there's no sharp threshold. No precise moment when you can say, now the branching has happened. It's gradual. The different parts of the superposition smoothly become more and more separated, more and more unable to interfere with each other. At what point do we say they've become separate worlds? There's no clear answer. It's like asking at what altitude the atmosphere ends and space begins. There's no sharp boundary. It's a gradual transition. Some physicists think of branching as happening at discrete moments, triggered by specific decoherence events. Others think of it as a continuous process, with the wave function constantly flowing and diverging into ever more branches. Both pictures are useful approximations, but neither is exactly right because the concept of branches isn't fundamental. It's emergent. Remember, fundamentally, there's just the wave function evolving according to the Schrödinger equation. Dividing that wave function into separate branches is something we do for convenience, to help us understand and interpret the mathematics. But it's not part of the underlying physics. The universe doesn't know about branches. There's just the wave function. So asking exactly how many branches there are, or exactly when branching happens, is a bit like asking exactly how many waves are in the ocean at any given moment. It depends on how you define a wave. The ocean is just water moving according to fluid dynamics. We divide it up into individual waves because it's useful, but the division is somewhat arbitrary. Similarly, we divide the wave function into branches because it helps us understand quantum mechanics, but the division is somewhat arbitrary. Different ways of dividing could give different numbers of branches. What matters is that the underlying wave function is well defined and evolves according to clear rules. The branches are just our way of describing it. That said, we can make some estimates. We know that decoherence happens extremely rapidly for macroscopic objects. A dust particle floating in air will decohere in a tiny fraction of a second due to collisions with air molecules and interactions with light. Larger objects decohere even faster. So, at the scale of everyday experience, branching is effectively instantaneous whenever a quantum superposition becomes correlated with macroscopic variables. And since quantum events are happening constantly everywhere, particles decaying, electrons jumping between energy levels, photons being absorbed and emitted, The total branching rate across the observable universe is truly enormous. Some estimates put it at something like 10 to the power of 10 to the power of 10 branches per second. Though this number is highly uncertain and depends on assumptions about the fine structure of quantum states. The point is, whether the number is finite or infinite, whether branching is discrete or continuous, the qualitative picture is the same. The wave function is constantly diverging into separate, non-interacting components. We experience one of those components as our reality, unaware of all the others. Now, let's address another common misconception. Does branching happen everywhere simultaneously, or does it spread out at the speed of light? Imagine a quantum measurement happening here on Earth. Does the branching occur instantly throughout the entire universe, or does it propagate outward from the measurement location? This is a surprisingly tricky question, and the answer reveals something deep about the nature of branches. Here's the thing. You can describe the branching either way, and both descriptions give exactly the same predictions. You can write down the mathematics such that branching happens instantly, everywhere, the moment a decoherence event occurs. In this picture, the entire universal wave function splits into two branches all at once, throughout all of space. Alternatively, you can write down the mathematics such that branching spreads out from the decoherence event at the speed of light. In this picture, the splitting propagates through space as the light cone expands outward from the measurement. Both mathematical descriptions are valid. Both make identical predictions about what any observer will see. There's no experiment you could do to determine which description is correct, because they're not actually different theories. They're different ways of describing the same underlying reality. And this tells us something important. The concept of branches, the division of the wave function into separate worlds, is not a fundamental feature of reality. It's a convenient human construct. The real fundamental object is the wave function of the universe. That's all that exists. And that wave function doesn't care about how we choose to divide it into branches. We can slice it up in different ways, and as long as we're consistent, we'll get the same predictions. This might sound frustrating. We want to know what's really happening. Is branching instantaneous or does it spread at light speed? But the answer is that the question doesn't have a definite answer because branching isn't a physical process in the usual sense. It's an emergent description of how the wave function's structure evolves. Think of it like temperature in a gas. Temperature is a useful concept. We can measure it, we can calculate it, we can use it to make predictions. But fundamentally, temperature isn't a thing. It's a statistical property of many molecules moving around. You can define temperature in slightly different ways, and depending on your definition, you might get slightly different values in unusual situations. But for most purposes, these different definitions agree, and temperature is a perfectly useful concept. Branches are similar. They're useful for describing quantum mechanics and understanding our observations. But they're not fundamental. They're emergent patterns in the structure of the wave function. And just like temperature, there can be some ambiguity in exactly how you define them, but that doesn't make them any less useful. So when someone asks whether branching is instantaneous or limited by light speed, the answer is that it depends on how you choose to define branches. Both definitions work. Both give the same observable predictions. The universe doesn't care which one you use. Now, another frequent concern about many worlds is that it seems to make everything meaningless. If every possible outcome happens in some branch, then my choices don't matter, right? Whatever I decide to do, there's a branch where I make the opposite choice. So there's no such thing as making the right decision or the wrong decision. All decisions are made by some version of me. This objection touches on deep questions about free will and personal identity, and I'll admit it's one of the more philosophically challenging aspects of many worlds. But I don't think it makes choices meaningless. Here's why. Even in many worlds, you still make choices. Right now, in this moment, you have preferences, values, goals. You want certain outcomes and want to avoid others. Those desires are real. When you make a decision, you're determining which kind of future self you'll become. Yes, other versions of you will make other decisions and become other kinds of people. But you can't control them. You can't experience their lives. All you can do is decide what kind of person you want to be, what kind of future you want to create for yourself in this branch. And that matters. It matters to you, the version of you reading this, the version whose experiences and memories form a continuous thread through time. Your choices shape your future, even if other versions of you make different choices and experience different futures. Moreover, not all branches have equal amplitude. If you make a good decision, one that's likely to lead to positive outcomes, then most of your measure, most of your quantum amplitude, ends up in branches where things go well. If you make a bad decision, more of your measure ends up in branches where things go poorly. So, in a sense, you're determining the distribution of your future selves. Making wise choices means that a larger fraction of your future selves will be happy and successful. Making foolish choices means a larger fraction will suffer consequences. That seems meaningful to me. Yes, there will always be some low-amplitude branches where unlikely things happen. Branches where your terrible decision somehow works out, or where your excellent decision leads to disaster due to some improbable accident. But those are rare. Most of your measure is in the branches where outcomes match probabilities, where good decisions tend to lead to good results. So you should still try to make good decisions, still act according to your values, still work toward the future you want. The existence of other branches doesn't change any of that. Another philosophical concern is about personal identity and caring about others. If everyone is constantly branching, then the people I love are splitting into countless versions. Which version should I care about? If I do something kind for my friend, there are branches where I do it and branches where I don't. So in what sense am I responsible for treating them well? I think this objection also misunderstands the situation. Yes, your friend is branching into multiple versions, but so are you. And the version of you in any particular branch interacts with the version of your friend in that same branch. The branches stay correlated. In branches where you're kind to your friend, they experience your kindness. In branches where you're cruel, they experience your cruelty. You can't hurt your friend in one branch and excuse it by saying that another version of you is kind to them in a different branch. Because to the version of your friend in your branch, you're the only version of you they'll ever experience. Your actions matter to them, regardless of what other versions of you are doing in inaccessible branches. So, moral responsibility doesn't disappear in many worlds. If anything, it becomes clearer. Your actions determine the experiences of the people you interact with in your branch, and those people are just as real, just as deserving of consideration as they would be in a single-world interpretation. The existence of other branches doesn't give you license to ignore their well-being. Now, let's talk about one more major objection, and this one is more technical. Some physicists worry that many worlds doesn't actually solve the measurement problem. It just hides it. The argument goes like this. In Copenhagen, the measurement problem is explaining why we see definite outcomes, instead of superpositions. Why does the wave function collapse? Many worlds says it doesn't collapse. The superposition persists, but we only see one branch because we're part of that branch. But here's the question. Why do we experience being in a single branch at all? Why don't we experience the superposition? If the wave function is really in a superposition of me seeing a live cat and me seeing a dead cat, why does my conscious experience correspond to one definite outcome? Some philosophers call this the preferred basis problem. When the wave function branches, it branches along certain directions in the space of possible states. But mathematically, you could decompose the wave function into branches in many different ways. Why does nature choose one particular way to branch? Why do we experience branches corresponding to definite positions and momenta, rather than weird quantum superpositions? This is a deep question, and I'll admit that many worlds doesn't have a complete answer. But it has the beginnings of an answer, and that answer is decoherence. Decoherence theory shows that when a quantum system interacts with a large environment, certain states are stable and certain states aren't. The stable states are the ones that don't interfere with each other, the ones that behave classically. These are the states corresponding to definite positions, definite momenta, definite numbers of particles. The classical properties we actually observe. Weird superpositions, like a cat being both alive and dead, or a particle being in two distant places at once, these are unstable. As soon as they interact with the environment, they decohere. The environment effectively measures the system, forcing it into one of the stable states. So the preferred basis, the way the wave function splits into branches, is determined by the structure of the environment and the nature of the interactions. It's not arbitrary, it's picked out by physics. That said, decoherence doesn't fully solve the preferred basis problem. There are still some subtle technical questions about exactly which states are stable and why. But it's progress. It shows that many worlds plus decoherence can explain why we see classical outcomes, why the world looks the way it does, without needing to invoke wave function collapse. Is the explanation complete? No. Are there still puzzles and open questions? Absolutely. But that's true of every interpretation of quantum mechanics. None of them have all the answers. The question is, which interpretation provides the best framework for making progress? And many physicists believe many worlds is that framework. It takes the mathematics of quantum mechanics seriously without adding extra postulates. It's conceptually clean, even if it requires us to accept a counterintuitive conclusion about the nature of reality. So here's where we stand. Many worlds says that the wave function never collapses. It always evolves according to the Schrödinger equation. When a measurement occurs, the observer becomes entangled with the system being measured. The wave function branches into separate, non-interacting components. Each component represents a different outcome. Observers in each branch see a definite result and are unaware of the other branches. This interpretation recovers all the predictions of standard quantum mechanics. It explains the Born rule. It respects conservation laws. It's mathematically consistent. The price we pay is accepting that we live in one branch of an enormous, possibly infinite, multiverse. A multiverse where every quantum outcome is realized somewhere. And for many physicists, that's a price worth paying for a theory that's elegant, deterministic, and doesn't require mysteriously treating measurement as special. So, if many worlds is so elegant, if it solves the measurement problem and requires fewer assumptions than Copenhagen, why isn't it universally accepted? Why do physicists still argue about interpretations of quantum mechanics nearly a century after the theory was formulated? The answer is complicated, involving a mix of scientific, philosophical, and even sociological factors. For one thing, many worlds makes no new testable predictions. It gives exactly the same experimental results as Copenhagen or any other interpretation. This means there's no experiment we can currently do to prove that many worlds is correct and other interpretations are wrong. In physics, we generally prefer theories that make distinctive predictions we can test. Many worlds doesn't do that. It's a different way of understanding the same mathematics, the same observations. So, from a purely pragmatic standpoint, it doesn't matter which interpretation you prefer. You'll calculate the same answers either way. This leads many physicists to adopt an instrumentalist attitude. They don't worry about what's really happening at a fundamental level. They just use whichever interpretation is most convenient for the problem they're working on. For quantum computing, you might think in terms of superpositions. For particle physics, you might think in terms of collapse. It doesn't matter because you're just calculating probabilities. But some physicists find this attitude unsatisfying. They want to know what's actually real. Not just how to calculate predictions, but what the theory is telling us about the nature of reality. And for those physicists, the interpretation question matters deeply. It's not just philosophy. It's about understanding what our best scientific theory is actually saying about the universe. For these physicists, many worlds offers a compelling picture. It says quantum mechanics is a complete fundamental theory. The wave function is real. It evolves according to the Schrödinger equation always. There's no collapse, no special role for measurement, no randomness. Just deterministic evolution of a mathematical object that contains all of reality. But accepting this picture requires swallowing some hard pills. You have to accept that you're constantly branching into countless copies, that most of those copies are forever beyond your reach, living in parallel realities you can never access or observe. That the version of you reading this right now is just one thread in an incomprehensibly vast tapestry of nearly identical but slightly different versions, all existing simultaneously. For many people, this is just too strange to accept. Even some professional physicists find it philosophically repugnant. They'd rather believe that the wave function sometimes collapses, even if we don't understand how or why, than accept the extravagance of the multiverse. There's also a historical factor. The Copenhagen interpretation was established early, taught to generations of students, and became the default way of thinking about quantum mechanics. When Everett proposed many worlds in 1957, it was largely ignored or dismissed. Niels Bohr, one of the founding fathers of quantum mechanics, reportedly wasn't impressed. The physics community had already settled on Copenhagen, and they saw no reason to reconsider. It wasn't until the 1970s when physicist Bryce DeWitt championed Everett's work and coined the term many worlds that the interpretation started getting serious attention. And even then, it remained controversial. Many physicists had already built their careers and intuitions around Copenhagen. Changing fundamental assumptions about reality isn't easy, especially when the new interpretation doesn't make different predictions you can test. So the debate has continued for decades. Conferences are held, papers are published, arguments are made, but no consensus has emerged. Different physicists prefer different interpretations based on their philosophical inclinations, their aesthetic sensibilities, their tolerance for ontological extravagance. It's less of a scientific disagreement and more of a philosophical one. That said, there are some hints that many worlds might eventually be testable. Some physicists have proposed experiments involving quantum systems large enough to exhibit superposition, but small enough to control precisely. If we could create a macroscopic superposition and keep it coherent long enough to observe interference between branches, that might favor many worlds over collapse theories. There are also theoretical attempts to derive the Born rule from more fundamental principles within the many worlds framework. If successful, this would show that many worlds is not just consistent with the Born rule, but actually predicts it, making the theory more powerful and potentially testable. But these are long-term prospects. For now, the interpretation question remains open, and that brings us to the really important question. What does many worlds mean for our understanding of reality? What are the implications of taking this interpretation seriously? First, and most obviously, it changes how we think about probability and determinism. In classical physics, the universe is deterministic. If you know the state of everything now, you can predict the future with certainty. Quantum mechanics seemed to overturn this, introducing fundamental randomness into the laws of physics. Many worlds restores determinism. The wave function evolves predictably according to the Schrödinger equation. Every possible outcome happens with certainty. The apparent randomness we observe is just because we don't know which branch we'll end up experiencing. From our limited perspective, it looks random. But from the perspective of the universe as a whole, everything is deterministic. Second, many worlds changes how we think about ourselves. You're not a single entity with one definite history and one definite future. You're a branching tree of nearly identical copies, constantly diverging as quantum events unfold. The you reading this sentence will, within microseconds, split into countless versions experiencing slightly different quantum outcomes. Most of those differences are tiny and inconsequential. An atom in your body decays or doesn't decay. A photon is absorbed by one molecule or another. Tiny variations that don't affect your macroscopic experience. But occasionally, quantum events have macroscopic consequences. A cosmic ray triggers a mutation in your DNA. A radioactive decay in your brain affects a neuron firing. These events branch you into versions with noticeably different futures. Over time, those differences compound. So there are versions of you out there, in other branches, who made different choices, experienced different outcomes, became different people. Some are happier than you, some are sadder, some are more successful, some less so. All of them are real. All of them think they're the only version. None of them are privileged or special. This raises profound questions about identity and what it means to be you. Are all those versions equally you? Or do you only exist in this branch, with this specific history? Philosophers have debated these questions extensively, and there's no clear consensus. But one thing seems clear. If many worlds is true, personal identity is not as simple as we thought. Third, many worlds changes how we think about the structure of reality. We're used to thinking of the universe as a single, evolving state. One timeline from the Big Bang to the present to the future. But many worlds says the universe is more like a tree, constantly branching into separate timelines. Or maybe it's more accurate to say the universe is a wave function in an abstract mathematical space called Hilbert space, and what we call branches are just different regions of that space that don't interact. Either way, reality is vastly larger and more complex than it appears. The observable universe, everything we can see with our telescopes, is just one branch, one tiny slice of the total reality. And that raises an interesting question. Could we ever travel between branches? Could we somehow access those parallel worlds and visit our alternate selves? The short answer is no. The branches are separated by decoherence. Once two branches have decohered, they no longer interfere with each other. They've effectively become separate realities. The wave function describing one branch and the wave function describing another branch are orthogonal in Hilbert space, which is a mathematical way of saying they don't overlap, they don't interact, they might as well be completely separate universes. To travel between branches, you'd need to reverse decoherence. You'd need to take two separated branches and bring them back into a superposition that can interfere. But this is almost impossibly difficult for anything larger than a few particles. Decoherence happens because a quantum system becomes entangled with a huge environment containing trillions upon trillions of particles. To reverse it, you'd need to track and control every single one of those particles, reversing all their interactions, unentangling them from the system. The amount of information you would need to gather and process is astronomical. And even if you could do it in principle, any attempt to interact with those particles to measure and control them would just create more entanglement, more decoherence. So, while it's not forbidden by the laws of physics in some absolute sense, it's so fantastically impractical that we can safely say branch hopping is impossible. The parallel worlds of many worlds are truly parallel. They never meet. But this does raise interesting possibilities for quantum computing. Quantum computers work by putting qubits into superpositions and letting them evolve unitarily without decoherence until you're ready to measure the result. In many worlds' terms, you're allowing multiple branches to coexist and interfere with each other, performing different parts of a calculation simultaneously across branches. Then, when you measure, you extract the result from one branch, but that result was influenced by the interference between all the branches. So, in a sense, quantum computers are harnessing the computational power of the multiverse. Multiple branches working in parallel, their results combining through quantum interference to give you an answer faster than any single branch could compute it alone. This isn't quite the same as branch hopping, but it's using the structure of the multiverse to our advantage. And as quantum computers get more powerful, we'll be able to do calculations that would be practically impossible without access to that parallel processing across branches. Fourth, many worlds has implications for cosmology. If the universe is constantly branching, then it's also constantly growing in some sense. Not in physical space, but in the complexity of its wave function. The Hilbert space containing the universal wave function has an enormous, possibly infinite number of dimensions. Each quantum system adds more dimensions. And, as the universe evolves, as particles interact and entangle, the wave function explores more and more of this vast space, creating more intricate patterns, more branches. Some cosmologists have speculated about connections between many worlds and eternal inflation, a theory that says the universe is constantly spawning new regions of space through quantum fluctuations. In eternal inflation, our observable universe is just one bubble in an infinite foam of bubble universes, each with potentially different physical laws. Could these bubbles be related to the branches of many worlds? It's an intriguing possibility, but the connection isn't clear. The branching in many worlds happens in Hilbert space, not in physical space. The bubble universes of eternal inflation are separated in physical space. They're probably not the same thing. But both theories suggest that reality is vastly larger than what we can observe, that our universe is just one small part of a much grander structure. And that's a humbling thought. Fifth, many worlds raises questions about fine-tuning and the anthropic principle. Our universe has certain physical constants, like the strength of gravity or the mass of the electron, that seem remarkably well tuned to allow for the existence of complex structures like atoms, stars, and ultimately life. If these constants were even slightly different, the universe would be lifeless. Some people take this as evidence for design. The universe seems fine-tuned for life, so maybe it was created by an intelligent designer who wanted life to exist. Others invoke the anthropic principle. If there are many universes with different physical constants, we necessarily find ourselves in one of the rare universes that allows for our existence. It's selection bias. We couldn't observe a universe that doesn't support observers. Many worlds adds an interesting twist to this debate. Then, many worlds, the physical constants don't vary between branches. All branches obey the same laws of physics. But there's a huge number of branches, and in different branches, different quantum outcomes occurred during the early universe. Some of those outcomes might have led to universes that are hostile to life. Others led to universes like ours. If that's the case, then the anthropic principle applies within many worlds. We find ourselves in a branch where the quantum outcomes were favorable to life. Not because those outcomes were likely, but because we couldn't exist in branches where they weren't. This doesn't fully solve the fine-tuning problem because it doesn't explain why the laws of physics themselves are conducive to life. but it does show that many worlds can naturally accommodate anthropic reasoning without requiring multiple universes with different laws. The branches provide the ensemble of possibilities that anthropic selection operates on. Sixth, and perhaps most, fundamentally, many worlds changes the relationship between mathematics and reality. In Copenhagen, the wave function is a tool for calculating probabilities. It's not necessarily real. It's just a mathematical device that helps us predict measurement outcomes. But in many worlds, the wave function is real. It's not just a representation of reality. It is reality. Everything that exists is part of the universal wave function. This means that reality, at its deepest level, is mathematical. Not just described by mathematics, but literally made of mathematics. The universe is a mathematical structure evolving according to mathematical laws. This idea has been pushed even further by some physicists and philosophers. Max Tegmark, for instance, has proposed what he calls the mathematical universe hypothesis. The idea that our universe is not just described by mathematics, but actually is a mathematical structure. And if that's true, then all possible mathematical structures exist, each one corresponding to a different universe with different laws of physics. This would be an even larger multiverse than many worlds alone suggests. Not just multiple branches within one quantum universe, but multiple quantum universes, each with different mathematical structures, different laws. Many worlds would be just one level of this hierarchy. It's speculative, of course. We're far from being able to test ideas like this. But it shows how taking quantum mechanics seriously, really seriously, can lead to radical conclusions about the nature of reality. Now, I want to step back and ask a more personal question. Should any of this matter to you? If you're not a physicist or philosopher, if you're just trying to live your life, does it make any difference whether many worlds is true or Copenhagen is true, or some other interpretation is correct? On one level, no. Your daily experience will be the same regardless. You'll still see definite outcomes when you observe quantum systems. You'll still experience one continuous timeline. The predictions of quantum mechanics, which have been tested extensively and are incredibly accurate, don't depend on interpretation. But on another level, I think it does matter. Because how we understand the nature of reality shapes how we understand ourselves and our place in the universe. If Copenhagen is correct, then the universe is fundamentally random. There's true, irreducible chance built into the fabric of reality. Things happen without sufficient cause. The universe is not fully deterministic, not fully knowable, not fully predictable. And we, as observers, play a special role. Our observations cause wave functions to collapse. We're not just passive witnesses to reality, we're participants in determining what becomes real. If many worlds is correct, then the universe is deterministic. Every outcome is predetermined by the Schrödinger equation. Nothing is truly random. It only appears random because we have limited perspective, because we only experience one branch. And we're not special. We're just collections of particles obeying the same quantum laws as everything else. Our observations don't collapse wave functions. They just entangle us with the systems we observe. These are fundamentally different worldviews. One emphasizes chance and observer dependence. The other emphasizes determinism and the vast scope of reality beyond our experience. Neither is provably correct, but both have profound implications for how we think about consciousness, free will, meaning, and purpose. If you believe we live in a single, probabilistic universe where your choices genuinely affect which outcome occurs, that might make your decisions feel more weighty, more significant. You're helping to determine the one true history of the universe. But if you believe we live in a deterministic multiverse where all outcomes occur, that might make you feel smaller, less important. You're just one thread in an infinite tapestry, and Your choices are all made by various versions of you across different branches. Alternatively, you might find the deterministic multiverse comforting. Every version of you is equally real. Your failures and regrets in this branch are balanced by successes in others. The person you wish you'd become exists somewhere. They're real. They're you. Or maybe you find that idea disturbing. If every version of me exists, then so do the worst versions. The versions that made terrible choices, hurt people, failed completely. Those are real too. They're also me. There's no escaping them. Personally, I find many worlds both humbling and exhilarating. Humbling because it reveals that I'm not as unique or special as I might have thought. There are countless near-identical copies of me out there, living nearly identical lives. But exhilarating, because it means reality is so much vaster, so much richer, so much more complex than it appears. The universe is not just what I can see and touch. It's an enormous, multidimensional structure, most of which I'll never experience, but which exists nonetheless. And I think there's something beautiful about that. About the idea that the universe is determined not by mysterious collapses and random chance, but by a single, elegant equation. That everything flows from the mathematics of the wave function. That reality, for all its apparent chaos and unpredictability, is at its core orderly and comprehensible. But I also recognize that this is partly an aesthetic preference. I like the elegance of many worlds. I like the philosophical clarity of having one rule instead of two. But liking an interpretation doesn't make it true. The universe doesn't care about our preferences. It is what it is, regardless of whether we find that satisfying. So, where does that leave us? We've examined the measurement problem, the paradox at the heart of quantum mechanics. We've seen how superposition and entanglement are real, experimentally verified features of reality. We've seen how measurement, the supposed collapse of the wave function, is the problematic part of the theory. And we've explored many worlds as a solution. An interpretation that says the wave function never collapses. It just branches into separate, non-interacting parts. Every quantum outcome occurs in some branch. We only experience one branch, but the others are equally real. This interpretation is mathematically simpler than Copenhagen. It requires fewer assumptions. It restores determinism. It treats observers as ordinary quantum systems. But it requires accepting a vast, perhaps infinite, multiverse. Countless parallel worlds beyond our reach. Many physicists find this convincing. Others find it extravagant. The debate continues because we can't currently test which interpretation is correct. They all make the same predictions, at least for now. So, in the end, which interpretation you prefer comes down to your philosophical inclinations. Do you value simplicity and elegance? Do you want the universe to be deterministic? Are you comfortable with the idea of parallel worlds? Then many worlds might appeal to you. Do you prefer to minimize ontological commitments? Do you think observers are genuinely special? Are you skeptical of untestable entities? Then maybe Copenhagen or another interpretation is more attractive. But here's what I think is clear. Quantum mechanics is telling us something profound about reality. It's not just a calculational tool, it's revealing the fundamental structure of the universe at the deepest level. And that structure is weird, really weird. Whether you interpret it as wave function collapse or branching into parallel worlds, quantum mechanics forces us to abandon some of our intuitive assumptions about how reality works. Particles are also waves. Measurement affects the measured. Distant objects can be instantaneously correlated. Cats can be alive and dead, or at least the mathematics says they can, even if we never see it. And many worlds takes that mathematics seriously. It says if the theory predicts superpositions, then superpositions exist, even for macroscopic objects. We just don't see them because we're entangled with them, part of the same branching structure. This is a radical claim, but it's a claim that follows naturally from taking quantum mechanics at face value, without adding special rules for measurement. And in science, we've repeatedly found that taking our theories seriously, following the math where it leads even when it seems absurd, often reveals deep truths about reality. Galileo said Earth moves, contrary to all common sense. Darwin said humans evolved from other animals, a shocking claim at the time. Einstein said time is relative, that clocks run at different rates, that the universe has no absolute present moment. Each of these ideas seemed absurd when first proposed. Each contradicted obvious facts of everyday experience. But the mathematics and the evidence demanded we accept them. And we did. And our understanding of reality expanded enormously. Maybe many worlds is similar. Maybe 100 years from now, it will be obvious that parallel branches exist, that the multiverse is real, that our inability to see other branches is just a limitation of our perspective, not evidence that they don't exist. Or maybe some new insight will show that many worlds is wrong, that there's a better interpretation we haven't thought of yet. Science is always provisional, always open to revision. But for now, many worlds stands as the most mathematically consistent, philosophically clear interpretation we have. It might be wrong, but it's worth taking seriously, because if it's right, it means we live in a universe far stranger and more wonderful than we ever imagined. A universe where every possibility is real, where countless versions of us are living out every potential future, where reality is vastly larger than what we observe, branching and diverging with every quantum event. That's not the universe we thought we lived in, but it might be the universe we do live in. And that's breathtaking. So the next time you make a decision, the next time you observe a quantum event, the next time you wonder about the nature of reality, remember this: you might not be alone. Other versions of you, separated by the thinnest of mathematical barriers, might be making different choices, observing different outcomes, wondering the same questions. You'll never meet them. You'll never know what they experienced. But if many worlds is correct, they're out there, just as real as you are, living in parallel worlds that emerged from the same quantum wave function that describes our universe. And all of this, all of these countless branches and parallel realities, all of it flows from one simple equation, the Schrödinger equation, telling the wave function how to evolve, completely, deterministically, beautifully, no collapse needed, no randomness, just mathematics, just reality unfolding according to the laws of quantum mechanics. That's many worlds, and it might just be true.